Welcome to this webinar on Fundamentals and Characteristics Application of a Parallel Beam Optics WDS on SEM by Bruker. My name is Max Patschke. I'm the Application Scientist for EDS at Bruker Nano Analytics in Berlin, and I will be the host for this session. Before we start, let me give you some housekeeping details. You should at this time be seeing the introductory slide on your screen. In the recording box. The presentation will last about 45 minutes. After the presentation, you can ask questions to our speakers. If we are not able to get to your questions during this live event, we will follow up with you by email. This webinar is also being recorded and will be available as on-demand version very soon. Let me introduce our first speakers, Stefan Böhm. Stefan studied industrial engineering at the University of Applied Science in Berlin and holds an MBA degree from the same university. He joined Bruker in 2007, and since 2011 he is working as a product manager for microXRF on SEM. Since 2020 he is also the product manager for WDS. Our second speaker is Dr. Michael Abrates. Michael studied geology at the University of Kiel and Göttingen, where he also acquired his PhD. During his academic career, he focused on analytical geochemistry using mass spectrometers and microprobes to analyze rocks and their minerals. Michael set up and managed a microprobe lab at the University of Jena before he joined Bruker Nano Analytics as Senior Application Scientist for WDS in 2015. So now let's get started. Stefan, please go ahead.
Yeah, thank you, Max, for the introduction. Good morning or good afternoon, everyone, from my side. First of all, brief outline of our webinar. First, we want to start with to discuss some principle of WDS and specifically for parallel beam WDS spectrometer on the SEM. Then we discuss a little bit of differences or synergies between EDS and WDS, and we'll highlight why this, which additional WDS brings for your analysis work. And then we move over to the applications where Michael will show you application examples from different fields. And also he will demonstrate analytical workflow for typical WDS measurement in the SEM. So let's get started with let me start with a brief introduction into wavelengths dispersive spectrometry. So WD spectrometry is based on Bragg's law of diffraction, what you can see over here, and that schematics here in the middle, where the lambda is the X-ray wavelength of interest. D is the crystal lattice constant of each individual crystal or diffractor, and theta is the angle of the X-ray incidence on the diffractor. So here is valid that the angle of incidence is equal to the angle of refraction. So therefore, the theory of WDS is relatively straightforward. The specimen excited by an electron beam, you can see over here, generates characteristic X-rays. These X-rays are diffracted by a diffractor with a well-defined 2T spacing, and the diffracted X-rays are counted here with a detector, which is in VD spectrometer, typically a proportional counter, and this detector is for sure part of the VD spectrometer. The geometry of a WD spectrometer is primarily adjusted by changing the angle theta of the diffractor relative to the sample, which you can see over here. That's the angle theta, or even here. This angle determines the X-ray energy that satisfies Bragg's law, and by adjusting the angle of the diffractor relative to the sample, a range of X-rays energies can be analyzed by using WDS. As you can see here on the left-hand side and on the right-hand side, there are two different spectrometer designs or design approaches. Both approaches are based on the same physical principles, which we just discussed. The image on the right-hand side shows the WD spectrometer design based on the Rowland circle geometry. This is more or less the classic WDS approach, and this approach is also commonly used in electron microprobes. The image on the left-hand side shows the WD approach based on the parallel beam spectrometer, which we want to focus here during this webinar. In the XSense, which is the Bruker WD spectrometer, a mirror optic, which you can see over here, is placed near the sample to transform the divergent X-rays from the sample into a parallel beam. This results in a relatively more compact spectrometer compared to a Rowland circle geometry, and also in a very high solid angle for all X-ray energies that can be detected with the XSense. This is because compared to classical Rowland circle geometry, the sample to diffractor distance is always the same for all X-rays energies. The XSense WD spectrometer Bragg diffraction takes place at the flat crystals, which you can see over here. Those individual crystals are located on a crystal turret. This is here the crystal turret. It has a specific drive, or has a drive for selecting the right crystal and to set the right Bragg angle. And the angle between the X-ray beam and the crystal surface of the crystal let it constant determines the X-ray energies that passes through the detector. So in order to fulfill the Bragg's law, the detector also needs to be rotated or need to be set to the right refraction angle. WDS results strongly relies on the optic alignment being at a proper working distance. So that means also in parallel beam spectrometer, the optic must be aligned properly with the sample at the proper working distance, so that the parallel X-ray beam is incident on the diffractor. If there are any diversions from the proper working distance, it can result or will be result in significantly reduced count rates, peak shape deformations, or degraded resolutions. The XSense spectrometer is equipped with an auto-optic alignment system, which is fully integrated in the Esprit software. And this auto-optic alignment system allows to compensate deviations in the sample positioning from the proper working distance by automatically adjusting the angle of the optic vertically and horizontally. You can see it over here. It can be adjusted automatically in three directions. So having that auto-optic alignment capability and the relatively more compact design of a parallel beam spectrometer allows the installation on the SEM, either on the WDS or on the on the EDS or even on the WDS port. You can see here a few installations here on the left-hand side on the Zeiss SEM, on the Hitachi SEM, and here on a Phi or Thermo SEM. Now let's compare some parameters, make a brief comparison of EDS and WDS, and I also want to discuss the XSense specs for this individual WD spectrometer. So what are the additional benefits which WDS brings? So first, from the physical point of view, there is no substantial difference between EDS and WDS, just the different detector abilities. So energy dispersive and wavelength dispersive X-ray spectrometry are complementary techniques, where EDS is measuring all elements simultaneously, so it's very fast. So it's better suited for everyday use, where the WDS is measuring the X-ray energies sequentially, so it's a slower approach, and also standard-based quantification is a must for a WDS. But the WDS brings a much higher peak-to-background ratio, which is important for the detection of low concentrations in the ppn range. And also the WDS provides much better energy resolution compared to a traditional EDS, which is important for resolving several peak overlaps. Here you see the specific specs for the XSense parallel beam spectrometer, because that's what I just discussed, is a comparison of general WDS compared with EDS. For X-Sense, which is based on parallel beam spectrometer, we achieve a very good energy resolution of 4 eV for silicon K alpha, and X-Sense PB spectrometer can cover an energy range starting from 70 up to 3.6 kV. So it's really sensitive in the lower energy region. And also, when we considering that the majority of peak overlaps are occurs in the lower energy region, the X-Sense spectrometer is capable to resolve all the peak overlaps in that specific energy range. The X-Sense can detect concentration down to 100 ppm. It provides a very large solid angle. And what you see here in green, it has an outstanding sensitivity for very light elements. So, for example, beryllium or boron. So, and with that, I want to move the microphone to Michael, and he will discuss the specific light element application and also trace applications with you. Thank you for now.
Thank you, Stefan, for handing over. And hello, everyone. I'm Michael, and I will present some applications. Before going into details, I want to summarize again the advantages of parallel beam optics WDS. And from this, we can deduce the application fields. So first advantage is the substantially higher spectral resolution typical for a WDS. Second are the enhanced peak to background ratios and therefore better detection limits for a WDS. And what is special about a WDS using a parallel beam optic is the outstanding sensitivity for the light elements. So with that, the WDS is an ideal technique to complement the EDS. So let's get started with some examples for spectral resolution. So here we see resolution in semiconductor material, resolution of tantalum M lines from silicon K lines. It's an easy task to resolve these peaks, even though they are less than 30 electron volts apart. The same for tungsten and silicon resolution. Tungsten M lines from silicon K lines, slightly above 30 electron volts. We can resolve in line scan in energy scans, but also in mapping. So we see here in red the tungsten, in green the silicon. Resolution of a sulfur K line from lead M lines. The resolution of these peaks in minerals, or resolution here of molybdenum L line from sulfur K line in a steel. So this is a steel that contains both elements, molybdenum and sulfur, and the WDS can determine the concentration and can detect both elements in steel, whereas the deconvolution of EDS cannot help for these low concentrations and narrow overlaps. Last example here, monazite. This is a mineral in some rocks, a mineral that is of economic interest and also of scientific interest for dating purposes. This mineral is a phosphate, so containing a lot of phosphorus. This is the high peak here on the right-hand side, and next to it is a smaller peak. The red marker here on the left side shows the yttrium L line. Even though these two peaks, phosphorus K and yttrium L, they are further apart than the other examples, so above 90 electron volts, but the small yttrium peak disappears in the tail of the phosphorus in the EDS spectrum. So WDS can resolve it, and we can determine the concentration of the yttrium of about 1% in this mineral. And with that, we go on with trace elements. Here is an example of a steel containing low concentrations of silicon, 0.5%, and of phosphorus, 0.02%. And with the example of silicon, we see why WDS is an advantage for trace element determination, and that is because of the high peak to background ratios. So we see a very narrow peak for the silicon, but also a very high peak to background ratio. When we compare the WDS range scan with the spectrum of EDS, we see the differences in peak to background ratio. And with this, it gets clear also only 10% of this peak, so 0.05% would still be easy to detect and to determine the concentration. Like what we see here with the phosphorus, 0.02% shows still a peak that can be determined by WDS. Some other examples, mineral, chromium, magnesium, aluminum oxide, and this mineral contains traces of zinc and traces of silicon, and with using the WDS, we can easily determine the concentration of these traces. Further, in mineral, this is plagioclase. It's a silicate containing traces of strontium, and so there's a real large problem for the EDS. It's not only because these two peaks are very close to each other, 30 electron volts apart, the silicon K line from the strontium L line, but it's further complicated by the fact that the silicon peak is very intense compared to the peak of strontium. So there's an intensity difference of 170 to 1. So this can only be solved by using the WDS, and we can even map the distribution of this trace element strontium within the mineral, so trace element mapping. And finally, we get to the third field of application, light elements. This is the plus of WDS using a parallel beam optics. And here we see results of the light elements from beryllium up to fluorine, comparison of the EDS and background and the WDS range scans in the foreground with the slightly darker colors. So we see differences in resolution, the narrower peak for WDS, but we also see differences in intensities. It's especially impressive for boron and beryllium, the difference in height of the peak, but even for elements such as fluorine, so the fluorine K line is about has a height of 300 counts per second for the WDS that we read on the right hand side. 300 counts per second compared to only 35 counts per second for the EDS. So almost 10 times higher intensity for the WDS, and the intensity difference between WDS and EDS for boron and beryllium is 200 times. So this WDS is very sensitive for the light elements. And some applications here for minerals. These 4 minerals that we investigated, albite, olivine, tuctopite, beryl, they are all silicates, so they all contain silicon. That means at low energies we can see the silicon L lines for these minerals. This is the olivine containing the least silicon, and here are the other minerals containing more silicon. So all show these silicon L lines at about 90 electron volts, and 2 of the minerals, namely albite and olivine, they contain no beryllium, but 2 other minerals, the tuctopite and the beryl, they contain beryllium at 109 electron volts, is the beryllium K alpha line. So these this peak or for beryllium K can easily be seen and can be distinguished from the silicon L line. This is what we can only do with the WDS. So we see here for comparison the EDS profile. This is a conventional EDS using a Mylar window. That is not very suitable for the lightest elements. Windowless EDS would be better, would show a peak, but it would not be possible to differentiate between the silicon L line and the beryllium K line. Some other examples, here's boron. Boron contents in glasses, silicate glasses. And we investigated 3 different glasses with different contents of boron, ranging from roughly 4% boron down to 0.2% boron in these glasses. We did not coat the glasses, but measured them uncoated in low vacuum. So also that is possible with the WDS measurement in low vacuum. And down to the lowest concentration, we could see a boron peak. So there is positive finding for boron. So this indicates here we are at the peak of boron K alpha, we are above baseline. Second example for boron is determination of boron in thin layers of boron carbide. These samples were contained boron carbide layers with different thicknesses ranging from 1 nanometer up to 50 nanometer. These layers of boron carbides were placed on a silicon substrate and covered with quartz glass. And these are the results of the range scans. And the results show an intense peak for the sample with the thickest layer, but still down to the thinnest layer, we can still determine, or we can determine the presence of the boron. We, at that inner energy of 183 electron volts for the boron K alpha, we could use 2 different multilayers, namely the 200 angstrom multilayer, which shows higher intensities. And that is easy to use for the thicker layers, so we have higher intensities. But for the thinner layers, it was better to use the 80 angstrom crystal or the 80 angstrom multilayer that showed a better peak to background ratio, though the absolute intensities are lower. So there is some scattering. It means it requires longer counting times that the applied 5 seconds per point. But even with this statistic, we see that the peak here is above baseline. So positive finding for boron, even in the thinnest layer of only 1 nanometer thickness. Let's go on with carbon. Carbon determination in steel. Here are 2 examples for 2 different steels. The steel on the left-hand side contains carbides, chromium carbides with contents up to almost 6% of carbon. These carbides are shown with green here, green for the carbon K alpha line. So high intensities of carbon here in the carbides, and the matrix is the steel, mapping for iron, L line. So mapping the carbides, that was an easy task. But even mapping of steel with 2 phases, no carbides, but 2 different steel phases, namely martensite and ferrite, with different carbon contents, 0.3% carbon in the martensite and 0.01% carbon in the ferrite. These differences can be mapped by WDS, and it shows here in green the higher concentrations of the carbon and the martensite. Red, this is the ferrite matrix, or the ferrite phases in this steel. So even those low absolute concentrations could be mapped because of the differences in the 2 phases. I'd like to point out that these mappings were done within only 5 minutes. That was enough to show the differences in the phases, and that was also required because at longer mapping times we get more contamination in an SEM. So it requires extra technical means like air jets and cold fingers to prevent contamination. Let's have a look on nitrogen. This is determination of nitrogen in trace level concentrations within a certified steel material. So we investigated several steels with different contents, ranging from 0.18% of nitrogen down to about 100 ppm nitrogen in the steel, and this x-axis shows the accepted values and the y-axis shows the measured values, and this line is the one-to-one line, and all the WDS measurements lie within acceptable values. They lie on this one-to-one line. So determination of trace level nitrogen contents in steel is possible, whereas for EDS, and these are the open circles, EDS, we are well below the limit of detection. So this is a limit of detection. So, but for WDS, the limit of detection is much lower. So 100 ppm nitrogen is possible to determine. And now the light element oxygen in 2 different samples. To the left, we see cast iron, and to the right, stainless steel. In the cast iron, we see here the peak for oxygen K line in the WDS range scan. We also see an indication for the oxygen in the EDS profile. So remember, these concentrations are trace amounts of oxygen. In the stainless steel, it's not possible to detect the oxygen with the EDS because there's a strong overlap with the chromium airlines. The WDS can resolve it. We see here next to the chromium airlines, we see the peak of oxygen, even though oxygen is present only in trace amounts in this sample. So here's the oxygen. And we will continue with an example showing the workflow, the measurement, or the application of the WDS. The WDS is fully integrated in Esprit. It shows up here in the configurator bar. The WDS in this case is at the moment switched off and can be switched on independently. It will measure along with the EDS. Here we will start the measurement by EDS. The sample we are looking at is zircon diboride. This is the ultra high temperature ceramic material used in aerospace applications. These particles of zircon diboride are placed in epoxy resin. And we will start the application with the measurement of EDS only. This is already the EDS spectrum showing zircon, the zircon L lines here. And yeah, also indication for oxygen, some oxidation or carbon coating of this sample. So there's carbon also. And let's start the video here. So we acquire a spectrum, and using the interactive quantification, we deconvolve the peak at low energy. And with deconvolution, EDS can give a hint for the boron. Now we apply the WDS, we make a measurement to prove if deconvolution is actually right. If we get more details, we switch on the WDS and measurement is started with with the 80 angstrom crystal, the 80 angstrom multilayer. The range scan is showing, it's acquiring more and more data. So we are changing the angle of the multilayer and acquiring the intensities at different energies. And now we see here two peaks, not only the zircon line, the zircon MZ line at this low energy of 153 electron volts, but also a second line for the boron K alpha at 183 electron volts. So here, this is resolution instead of deconvolution, resolution of showing the presence of the two elements by these two different peaks. And after this range scan, we will now start a mapping for two elements for the boron that we already identified. So we find the boron in the particles shown here by the green color, mapping for boron K alpha. Then the energy is changed here. The crystal angle is changed to from 183 to 277, and that is the energy of carbon K alpha. And this will be the second cycle of mapping. Now we are mapping for that energy. So, and this carbon is mostly present in the matrix of the sample around the zircon borite grains. So this example shows that WDS is energy selective. So mapping is sequentially. And with that, we come to the summary and conclusion with a focus on the applications. So there are three fields of applications for the PBO-WDS. The first application field is with high spectral resolution. We can resolve peak overlaps that EDS cannot resolve. And second field, trace elements. Because of the high peak to background ratio, we can determine low concentrations of elements down to 100 ppm and even below. And third, which is special because of the optic close to the sample, the high solid angle. So this is special for only those WDS having a parallel beam optic, especially the grazing incidence optic that we are using. And that is the high sensitivity for low energies, low X-ray energies, so high sensitivity for light elements. And we can determine light elements from beryllium on. So that is an application field for this type of WDS. And with that, I would like to thank you for your interest and hand over back to Max.
Thanks, Stefan and Michael, for these excellent presentations. We will have now our question and answer session, which will last about 10 minutes. So, but first a quick reminder to our viewers, you can submit a question by entering it to the according field on the right side of your screen and pressing submit. So if you have a question, please go ahead. In the meanwhile, we've already had a number of questions coming in, so I will get started by asking the first questions, maybe to you, Michael. The question is here, what are the typical count rates for light elements like carbon, bore, or beryllium you can achieve with WDS?
Yeah, that's a good question. So count rates at these low energies are higher than count rates for the higher X-ray energies. This is because of the large solid angle, because of the optic being very close to the source of X-rays. And this is also, these count rates are also high because of the multilayer elements, which give high count rates. So it's especially high for beryllium and boron. But also for carbon, it's high. This is a number I remember because we specified 900 counts per second per nanoampere with the 80 angstrom multilayer. So don't compare that with the 100 angstrom multilayer that would give higher count rates, but also worse resolution. So yeah, 900 is the minimum, but in practice it's often much higher, like the double.
Okay, thank you. Then we go to the next question here. Or maybe I put the two questions together. They go a little bit together. So can you compare the light element sensitivity of WDS with EDS? And yeah, what is possible with WDS?
Yeah, so compared to a normal EDS, it's yeah, like I showed here, up to 200 times more sensitive than the EDS. Compared to windowless EDS, it's also more sensitive for the lightest elements, so it has a higher efficiency for boron and beryllium. But the advantage is then also the resolution of close peaks at these low energies. Yeah, and the second part of the question was?
So what is possible with WDS? And so you need low KV
Low
analysis for light elements. So and what is possible with WDS?
Yeah, about the low KV, that is generally an advantage, or it's generally required to use low KV because of the quantum efficiency that's higher at low KV. So if you are interested in the light elements, you should apply 5 kV or even lower, and it's no problem to apply low KV as low as maybe 1 kV. But you have to keep in mind that with a lower excitation or a smaller excitation volume, you get less signal. So that requires longer acquisition times.
Thank you. And there is another question here also. Can with WDS separate titanium and nitrogen or bore and chlorine?
Titanium, nitrogen, that is difficult because the energy difference is one is at 392, the other 395, so only 3 electron volts difference. Yeah, so that is challenging. Yeah, exactly. So yeah, that is really difficult, and I doubt that. So it's too close. So at these energies we have what is it, like half width for the peaks of nitrogen, like 10 eV. So that is probably too difficult.
Okay, thank you. And then maybe here one more question for you, Stefan. So the WDS chamber, is it under vacuum?
Yeah, thank you for the question. Yeah, also the WDS chamber is under vacuum. So, what we have in the WDS is most of the time equipped with a so-called gate valve, which separate the pressure from the SEM chamber from the WDS chamber. So when the gate valve is closed, you can vent the SEM chamber by keeping the vacuum in the WDS chamber. So that allows you so that there's no additional time needed to pump up both chambers, because the WDS chamber can always stay under vacuum, or even when the SEM chamber is vented, also the WDS chamber can be vented.
Okay, then thank you very much, Stefan and Michael, for this excellent presentation. Unfortunately, we run out of time and will conclude our question and answer session for this webinar. But yeah, as a reminder, today's event has been recorded and will be available for viewing very soon. So thanks for being with us today, and we hope to have you soon again in the future for the next webinar. Goodbye.